Hello everyone, this is Spencer Snowling from Hydromantis, and I'd like to thank you for joining us for today's webinar about using the gpsx optimizer function. So, as you know, if you've been to some of our webinars before, this is an opportunity where I'm going to make a presentation and you can ask me some live questions as we go along. There should be a questions panel as part of the GoToWebinar panel dashboard that you're using today. So please type your questions in there as we go along. I'll hold all the answers until the end, and we'll have a bit of a live question and answer period. But feel free to type in your questions along the way. So if I haven't met you before, my name is Spencer Snowling. I'm VP of Business and Product Development, and I've been the developer of gpsx for about the last 10 or 11 years now. And today's webinar is going to focus on one of the advanced features of gpsx called the optimizer. So we're going to start by talking a little bit about numerical optimization, talk about how it works within the gpsx context and how you can use it, and how to go about doing an optimization, how to set it up. And I'm going to run a couple of typical examples for you for the two different types of optimization that we can do in gpsx. And then, as I mentioned, we'll have some questions and answers at the end. So essentially, from the point of view of doing a simulation, an optimization is basically a search routine. It's a procedure for finding the best set of parameter values that can perform a desired function for you. So you set up an objective function, your objective being to maximize something, to minimize something, or to fit to a bunch of data points. And then you let the gpsx optimizer have control of a couple of parameters or several parameters if you like. And then it will try to minimize or maximize as you see fit that objective function. So in most cases, if you're trying to fit to some given data points, that's really looking at this measure of the prediction error. So that's the difference between the simulation itself and a bunch of data points that you have measured and entered into that gpsx simulation. Now that can be for anything in the model. It can be for an effluent concentration. It could be for OUR. It could be for, well, pretty much any parameter that gpsx has in it. So you set that up, and then you run your simulation, and then it can try to find the best set of parameters to meet that objective that you've set. So it could be minimizing an effluent concentration, for example. So typically there are two different kinds of optimizations that we do with this automatic feature in gpsx. One of them is, the first one, more straightforward, simple one, is to use it for calibration. And in particular, trying to do parameter estimation by fitting to a number of data points. In this case, and I'm going to show you this example in a moment, we're going to fit the simulation to some batch data for a situation where we have a bioreactor with a certain amount of substrate in it, and that degrades over time. We're going to be able to adjust the maximum specific growth rate and the half saturation coefficient, and then see how that affects the simulation. And so we're going to adjust those, or we're going to have gpsx use its search routine to adjust those and find the best set of those two parameters that can give you, the best fit for that curve. So that's where you're trying to fit to a time series of data. The other one, and this is probably the more useful one, is to have it find the best set of operational parameters for your particular wastewater treatment plant in order to do some sort of minimization or maximization. So in other words, find the best possible combination of step feed fraction and RAS flow, or whatever other combinations, flow splitting, tapering of your aeration system, any of those types of parameters. Let gpsx have control of those and find out what you can do to get that best minimum concentration in your effluent. So in this case, we can see here that there was some sort of obviously heavy change in loading to this plant, and normal operation would have produced a line up here, but we can let the gpsx optimizer run, and it's making changes to those parameters and getting progressively better answers as it moves along. So how do we do this? How does it work? First of all, I'm going to tell you how to set that up in gpsx, and then we're going to show you an example, and then I'm going to actually run through a little bit of the detail about that, how that optimizer routine works. So the first thing you have to do is pick the parameters that you want gpsx to have control of. So obviously these should be things that are going to have some specific effect or some direct effect on the thing that you're trying to optimize. So in this case, we're going to do the parameter fitting example first. So we're going to allow it to have control of the maximum specific growth rate and the substrate half saturation coefficient. And over here, where normally you would have had a slider, you'll now use the optimize function. You then have to set the objective function, and I'll show you where you do that in the software itself. You give it its target. Basically, you pick the thing that you want to build your objective function around, and then specify the data that it should be trying to fit to. And then when you run your simulation mode, when you're in simulation mode, you select the optimizer on, and then you run your simulations. And what you'll see is kind of like the analyzer feature that we also have. gpsx runs a number of simulations over and over and over again while making changes to those parameters for each iteration, and then trying to see, based on what the evaluation of the objective function is at the end of each run, it makes changes and moves around and tries to get that best set of parameters. Okay, so that's a lot of talking. Let's actually take a look at this working in reality here. So I'm going to start my copy of gpsx here. And there's a number of optimizer examples that are available built into the software here. So I'm going to actually use, just for an example right now, the layout that we built for tutorial 8 as part of gpsx. So just to quickly show you how that would be set up, if we go here, this is the optimize button, by the way. If we go down, we can look where we can pick the different types of optimizers that we can do. We can take a look at the different forms of the objective function, but the most important thing to set up at the beginning is your target variables. So I turn optimizer mode on, and in this case, we are trying to fit the soluble substrate concentration. So I go to my state variable menu, and you can see here that one's been checked off. This has already been set up for us. You can check off multiple target variables if you like, and your objective function will be calculated across several of those. But in this case, we're just going to use this one particular variable. So we are going to try and get the readily biodegradable substrate concentration to fit as close as it can to the data that we have measured. Okay, so if we go over here to simulation mode, and we can see that we've had those two parameters put up here, and as indeed I mentioned before, we've got these set to the optimized value. So this is now, you'll notice that the knob, so to speak, of the slider is now missing, and it's turned green. This meaning that gpsx has control over these two parameters, and we'll be making changes to those values based on how well it's doing while it's trying to fit that data. So I'm going to run it once here without the optimizer on, and we can see what that very first initial guess looks like. So as you can see on the right here, here's our data points. That's been a data file that was actually specified for this particular situation. So this would be something measured experimentally, for example. And that's been specified when we run this simulation. And we can see here that it's not a great fit. Of course, the model's under-predicting the concentration through pretty much the entire run. Now, if I were to rerun this, make changes to those parameters, that line would move around and we would get something a little closer to the data points. But I want the gpsx optimizer to do that for me. So what I'm going to do is I'll go up here, I'll turn on optimize mode, and just because this runs really, really fast, I'm going to put a delay on this just so that you can see it, because otherwise it will go by so quickly, and I don't think the GoToWebinar would react quite quickly enough for you to see the whole thing. So what I'm going to do is I'm now going to rerun that, and you'll see a number of simulations being plotted one after another. And we're keeping about the last 4 or 5 of these simulations on the screen at any given time. And you'll notice as this is running that it takes changes up here to the parameters that we have specified. And as we're doing that, we can see what those plots on those simulations are like. And if you've been following this, you'll notice that it took several fairly poor guesses to start with, and then as it collected up more information, it did a better job, and now it's sort of converging in on that final value. So what it's doing is each time it makes an update to these parameters, it runs its simulation, it recalculates the objective function, which in this case is looking at the difference between the simulation and each of these data points, and it sums it across all of the data points that we have available. And then it improves the guesses for the next iteration around and around. So eventually this is going to stop based on a termination criteria. There are several of those that you can control. Basically, when the changes here and the parameters become very small, or when the value of the objective function itself becomes very small, meaning that the change in that is small, and it's not improving its guesses over time, then it brings it to a halt. It can also specify a maximum number of iterations as well. And you can see here pretty much we're plotting the same line over and over again with very small changes. And so this is what the optimizer feature can do for us. I'm going to set up so that it finishes up its last run there. And we can see that now it's fit that line about the best that you're going to be able to do in this case. So that's a good parameter fitting exercise. And you can see how that now originally from our original guess of I think it was 2 and 2.5 or something like that, we've now got a much better estimation and, of course, a much better fit. Okay, so let's go back to our slides and talk a little bit about the actual way that we do this. So we use the simplex method for doing this parameter search. This is an unconstrained optimization method, and it works well for any number of parameters that you want to do the optimization for. Certainly it works better when there's fewer parameters to optimize, but there's nothing stopping it from using more than 2 or 3 or any number that you like. It uses only the function evaluation, meaning that we don't have to run a lot of simulations to find the values of derivatives of all of the relevant parameters. It does it by taking the number of parameters plus 1 and evaluating those, and then taking some techniques to optimize its search from there. The reason we use this particular one, there are more sophisticated ones than this, is because it's really well suited for problems that are not very linear or have a number of discontinuities. And as those of you who have used the activated sludge models, the ASM models over a period of time have known they are very complex. They can be very nonlinear in some cases, where especially when you're dealing with situations where you're sort of partially nitrifying, that can be really huge changes right sort of at those borders, and a number of discontinuities, specifically if you're using simulations where you have something that cycles through a number of periodic steps, like the sequencing of an SVR or something. That kind of situation where things can be very complex dynamically, this methodology works quite well. It's a bit of a brute force method in the sense that sometimes you have to run a lot of simulations, but it gets the job done. So a simplex in this particular case is a geometrical figure consisting in dimensions of n plus 1 point. So the example that I just did had 2 parameters. So in 2D, which is nice to be able to show you what's going on here, in 2D we will have a 3-point geometrical figure. So that's a triangle, obviously. So we're going to do a 2-parameter optimization, and we're going to try to do the example here, the explanation, to find the values of those 2 parameters, the growth rate and the half saturation coefficient, such as this particular parameter is minimized. This is a sum of squares of the error in our simulation. We're going to try and minimize this. So the example that I just did for you is basically this problem. So the way that the simplex works, the simplex method works, is it does 3 evaluations right off the bat. It starts at the values that you give it in the initial section. It makes a change to 1 parameter, then it makes a change to another parameter, and evaluates those 3 points. It looks at which one of those 3 values is worst, which is the one that has the largest error, and then it flips that point through the other 2 and projects out the other side. So if we had 3 points evaluated and it said this is the one that has the largest amount of error, given that we're trying to minimize error, I'm going to project this value through the middle of this side, and I get a new point out here. Now that's my new guess. It may or may not be better, but theoretically most of the time it should hopefully be better than at least all 3 of these guesses on this side. So that's the way it works. You just continue to flip and project through to the other side. Now, our version that we use in gpsx has a number of other additional features. We immediately take a look and see, is this spot better than the 3 that we were working from before? And if so, let's expand it on that same direction. So sometimes we tack on that expansion right away. Sometimes we'll find out, no, it's not actually better than all of these 3, but it's better than some of them. So we're going to take another contraction here, sort of in the middle part. This helps to get it to converge to a final answer more quickly. And eventually, if you do it enough times, over and over and over again, moving around, you do eventually converge on an answer. So I like this example. This is probably the easiest way for you to visualize this in this animated slide. So here's our growth rate and half saturation coefficient, and these other items, these rings here, sort of show the value of the objective function, the value of that error as a surface. So the 50, this spot over here is very high, and basically this is the target. This is where we're trying to get to here in the middle of that value of 10. So we start out with 3 guesses. We take a look at those and we can see the 3 runs that were done by the optimizer, and it says, so clearly, this one at 0 is the worst. So I'm going to project through to the other side and see, is that better than the other 2? Yes, so we'll project again and again, and it seems to be doing a better job. It's going downhill, so to speak. And we get a continuous improvement here until we sort of pass across this little valley and we start going back uphill again. Now this guess was worse than these 2 that are over here. So it knows to make a change. So it backs up and reflects the other way and also does a contraction in this particular case. And it keeps flipping and it keeps contracting and making better guesses and so on until we get to the point where it has converged on the correct answer. So that's kind of a visual interpretation of what our gpsx optimizer function is doing. There are a few other little bells and whistles built in as well, but they are there to sort of improve the efficiency, to make it not get sort of hung up on bad answers and so on. But that's basically the essence of what it's doing. Okay, so I'd like to run another simulation for you right now and do another example. So let's close this one and go to the sample layouts menu, and you can run this on your version of gpsx to be able to play around with this. And go down here to the process optimization example. It's part of our sample layouts menu, and it's an example of an alternating aeration system. So you'll see here, I'll just quickly give you an example of what this was about. This was actually based on a real project that I worked on about, boy, it must be 9 or 10 years ago now, for an industrial situation. So I've modified the layout a little bit to make it work for municipal concentrations. And this was a CSTR clarifier, pretty conventional activated sludge, except that it had an aeration controller, and they were setting a cycle so that it would aerate for a period of time and then turn the air off and let it be anoxic for a period of time. And they were trying to maximize total nitrogen removal by getting nitrification and denitrification in the same basin. And they did that through this cycling system. So what we were hired to do in this particular case was to see what kind of an improvement could be achieved, and then as part of that, we chose to use the optimizer as a good example of the way that we could find what is the best settings that we could get for this particular system. So what I'm going to do is I've put the 2 parameters up here that are part of that aeration controller. So one being the total length of the cycle time, and the other one being how much of that time is the aeration on. So right now, I'm saying for every 3 hours, I want the air on for the whole 3 hours. So this is complete full aeration all the time. The ammonia coming into this plant, by the way, is about 24 or 25, I think. So when I run this simulation, we can see here that from this graph that we're getting pretty much full nitrification for the SRT that we're running at. We're generating nitrate. And here's our total nitrogen that's coming out of the plant. It looks like it's about 24.7. So remember that number in your head, 24.7. That's what the situation is like if you aerate all the time. So what happens is, in this particular case, if I was using a slider and I was just trying to do a bit of straightforward modeling analysis, I could run these simulations over and over again, and I could start playing around with these numbers and trying to find the number that decreased this down to the lowest level possible. If I knock off a little bit of air there, then it starts to reduce the nitrates. We get some denitrification happening. If I lower it down too low, though, then it doesn't nitrate. It doesn't nitrify. We can see we've got lots of ammonia here, and our total nitrogen comes way back up again. So what we want to find out is that best combination of total cycle time and the amount of time, the fraction of the time that it's on during that cycle. So let's put the optimizer on. I'll set up those 2 optimized variables there, so you can see those are turned green. I'm going to turn on that optimizer feature. I'll also let you know that I've set up a total nitrogen as the target variable here. we go up here, look at target variables. There's the final effluent for total nitrogen. And I've set up a file in the background with a target total nitrogen of 0. That's the nice and easy, straightforward way to get this thing to do a minimization. Basically, we're going to try and force total nitrogen to go towards 0 as far as it possibly can. Okay, so let's run this with the optimizer on. So I do that. I turn on the optimizer here, and let's run it. So what we'll see is, oops, pardon me, I've got to reset that. I left it over at my old values there. Just let me reload that simulation again. All right, turn this on, and we'll run that again. So you can see here now it's starting to change to these parameter values. It's running it as it is. And so we've now converged to a final answer. So if you remember before, we were way up here with a total nitrogen in their effluent of about 25, and now it's saying the best combination that the gpsx optimizer could find is at about 17. So this is the optimal setting. So for it's saying that for every 4 hours, 4.75 hours, we want the air on for 2.14 hours. So that's obviously pretty precise. It's done it in a completely mathematical format here, but that's the idea behind using it for a process optimization. So you can imagine that if I had a different set of parameters up here, if I had a plug flow tank and I wanted to do the split of the aeration, or if I had a dynamic event where I wanted to do some step feeding and I didn't know what the fraction should be, I can get that maybe done through the optimizer. I've seen it used in a number of different ways, particularly for settings where you have parameters that are maybe not intuitively connected to each other, and you want to know how one is going to affect the other, you know, recycle rate and aeration distribution and so on. So this is a fantastic tool to be able to sort of get a feel for what the relative optimal settings could be for your particular system. It's something you could arrive at if you played around with it long enough, but this will give you a sort of a direct numerical path to getting that answer. All right, so I have a few more slides here to conclude. Just saying a few things about using it. There are a number of different types of optimizations that you can do. I've been showing you just the time series example so far. You can actually do it on probability if you have a number of data points and you want to try to move around the probability and the likelihood of all those points falling on one side or the other. You can do it that way. We have a dynamic parameter estimation package too, so it does it in stepwise pieces through the length of a dynamic run. I'll show you a slide on that in a moment. And we can do it for different types of objective functions. I was showing you the absolute sum of squares version there, but you can use all these other different ways to define your objective function and the way that you measure your error. So here we can see there's a number of settings that you use for the termination criteria I mentioned before. Basically, it's the point at which it's going to stop its convergence. So you can either do it based on the amount of parameters, you can have a total number of iterations. It basically takes whichever one of these happens first that brings it to a halt. And there are a few things that you can run into when you're doing this. Sometimes you'll find it may get sort of hung up on a particular answer, particularly if you're finding that the parameter, one of the parameters that you have, is stuck up against one of its boundaries. So just like you have on your slider when you can move to the left and right, you specify a minimum and maximum value. Well, the same thing happens for the optimizer as well. Sometimes if you get stuck up against one of those boundaries, it can make the optimization kind of inefficient. So as I mentioned earlier, there are a number, you can use any number of parameters that you want. It's theoretically unlimited. However, having used this for many years, and I actually used this feature quite a bit when I was doing my PhD way back when, the practical experience does that really about 3 parameters is sort of the maximum practical number that you can run with. If you want to use more than 3, it can happen, but in reality, really 2 or 3 of those parameters will drive the simulation forward and will really drive that optimization. So you sort of fit 2 of them well, and then the third one might be any number. So it's basically a few things that you need to keep in mind. You want to make sure that your initial conditions are good. So those are the first values that you've entered into the parameters that you're performing the optimization on. You have to make sure that the parameters that you're optimizing do have some sensitivity in the simulation. So if you're performing optimization on parameters that don't really affect the effluent that much, then obviously you're not going to have a very optimal situation. So, and because you're running a large number of simulations, you can really generate a lot of data if you're going to hold on to the data from each run. The good thing is that a lot of that data has been very well processed, and you'll note here when you're after the data has come out, I didn't illustrate it to you earlier, but you can get quite a statistical analysis. This is work that was done by my colleague Oliver Schra. Once the analysis is complete, this information gets output to the command window. And this is kind of a histogram in a way, looking at each of the data points that you've provided. It sort of shows you this tree where you can see which side of the simulation that the residual data point lands on. So these are a distribution of your residuals, and you can see that some fall on the left and some fall on the right. So if you had systematically everything on one side, that would show you that while numerically your objective function met your requirements, you're probably not a good simulation because you'd be sort of systematically under or over predicting your values. I'll mention briefly the dynamic parameter estimation tool. This is basically the same thing, but just done on a stepwise window as it moves along. So this would be a case where it's running along and it has a little window here of 0.1 days, and what it does is it performs the optimization just inside this little window, running a simulation that starts from the end of the previous point, and it's making adjustments to a parameter, and it's trying to fit to this data. Once it's converged, it then moves on to the next step. And so you can do that to get a time-varying value of your parameters in order to be able to see how they drift or maybe move around with time. In this case here, we can see that this is a very tight fit, and we've got some values of this parameter that are being output along with the simulation. So a few quick final thoughts. This is really a very powerful tool. It requires a fair bit of setup and some understanding of how your model's been put together, but it's there for you to use in the gpsx Pro package. So it's always good to try and start simple. Do it with a single parameter, maybe just to get an understanding of how it works. Always good to do a few investigations first to make sure that the parameters that you're trying to optimize actually do make an effect in your model the way that you hope that they will. It's appropriate to remember, I suggest that you try to put in appropriate constraints for all of the values that you're putting up in the optimizer control. To make sure, it's sort of just blindly looking at the math. You want to make sure that if you're trying to, say you put an SRT set point up there, you want to put it in a range that's appropriate for whatever your client's been designed for so that it doesn't go outside the bounds of reality. And try starting from a few different initial conditions just to make sure it comes up with the same answer each time and that you're not sort of drifting off into what we call a local minima, meaning that it sort of took a little path into a little low spot at one point in the simulation or one point in the area that it could overall investigate, even if there was a lower point somewhere else. So what we do have a few things that are built into the model where it will occasionally take a large step outside as it's kind of coming down to its final convergence, just to make sure that it's not hung up in a sort of a local answer and try to find that sort of global best answer for you. So as I mentioned, if you'd like to look at this in more detail, tutorial 8 is an excellent example of doing that. And you can see how that is all put together, and you can run that yourself and see how that works and play around with your own models. So I'll have a few quick words about a few things going on here at Hydromantis right now, and then I'll move on to the questions. If you have any questions, please type them into the box available on your dashboard. So first of all, I'll remind you that we got our YouTube channel up and running, and it's now fully populated with all of the videos that are previously available on our website. You can still actually get to them through the website as well. If you go to youtube.com/Hydromantis, you can find all of the tutorial videos for all of our software products that explain how to use the software, and it takes you through. They're all animated and narrated by our staff. We also have recordings of all of the webinars in the past, and so I'm recording this one today, and it'll be up here very shortly. We also continue to offer online training. So if you were looking for gpsx or CapThatWorks or ToxChem training, we can provide that to you using the GoToWebinar service that we're using right now. It's a nice and easy way to have a group of people on your end receive training, and we'll do it live and answer your questions from here. I'll briefly mention that we are in the midst of development of 3 of our products. I've been working quite a bit lately on gpsx version 6.3, adding some new software features for data processing and a couple of new activated sludge aeration models that will be part of that package. That will be available a bit later in the year. ToxChem should be available somewhat before that, and we're also working on version 3 of CapThatWorks. So our next webinar will be on June the 18th at 2 p.m. in the afternoon. And this will be one that is for people who either are new to gpsx, or new to any of the, new to Hydromantis, new to activated sludge modeling. It's very much a back to basics sort of introduction to the very basics of modeling and how to set up a model in gpsx and run some simulations and so on. So back to basics is our next one, and you can pop over to our website, click on the webinars tab, and register for that if you like. So I'll say thanks very much, and if you want to hang around, I'll answer a few questions. If you are unable to stay with us, I thank you for coming, and I hope to see you soon.